Okay, here we are going to talk about the effect of weed density, leaf area, and the leaf area of the weeds on crop yield. We are also going to talk of the effects of relative cover on crop yields. So there are three things which we may look at in the first part: weed density, relative leaf area, and the relative cover. So, in order to understand the effect of weed density on crop yield, there could be need to carry out some studies or to do some experiments. And most of the common experiments which are done, number one, we've got the additive designs, then the replacement series. Number three, we've got addition series or response surface. Number four, we've got dialer experiments. And number five, we've got the enabled experiments. But I think for breeders and the agronomists, I think you may just want the additive designs and the replacement series. We'll find out why these are very important. For these lectures, we may leave out number 3, 4, and 5. So let us talk about the additive experiments. Why are they important? They are important because we may want to answer the following 3 questions. If we are managing weeds, we want to know the minimum weed density which can justify weed control. So the additive experiment can answer this question: what is the minimum weed density which justifies weed control? We also want to know the most competitive weed, and also to have an idea about the crop yield loss. So the additive experiments can address these questions. And indeed, these 3 questions are important when it comes to weed management. You can do the additive experiment in pots, as you can see it on this picture. We have got pots with maize and L-cine indica, which is Rapoko grass. The idea was to determine the effect of Rapoko grass or L-cine indica density on the maize. We also have another experiment which determined the effect of Tithonia rotundifolia density on maize growth. Now for the additive experiment, Number one, it's known as the additive experiment. We are now talking about the kind of treatments which are required in an additive experiment. You can vary the width density. For example, from 0, 2, 4, 6, 8, 10, and 12 plants per pot, while the crop density is held constant. For example, you can just keep one maize, one crop plant per pot. The treatments have to be replicated in an RCBD or a CRD. Data collected, it could be crop height, crop biomass, leaf area, and the weed biomass. But for your own information, the most important parameter is crop biomass. That is the most important parameter. Now, when you have got your data, we can use graphs and regression analysis to explain the data. Usually tables are not suitable. Now, when you have drawn your graphs and done regression analysis, in most cases, we end up with linear relationship. Quadratic response is rare. Exponential curve, we can get it. The hyperbolic curve is very common. Then the sigmoidal curve, sometimes we can also get it. So what I'm going to do is probably try to explain step by step. Let's suppose you've got your weed biomass and you've got the weed density. What do you want to use these parameters for? You want to find the relationships, which could be from number 1 up to 5. And how do we do it? So let me move on to another area. So we are talking about the additive experiment. So the objective number one, we want to determine the competitive ability of the weed. For this, we need two parameters. I, which is the slope, and A, which is the maximum crop yield loss. So we want this competitive ability of the wheat, which is determined by these two things. Objective number two, to determine the weed control threshold. This is the weed density that justifies weed control. So the parameters which you get from the additive experiment important parameters weed density, and crop yield. Or biomass. So we use graphs to relate these parameters. Another parameter which we may compute is known as the crop yield loss. So we will need this, we need this and that, and we can draw graphs which can relate weed density versus crop yield, then weed density versus crop yield loss. So if we have a weed density here, and the crop yield, we may get something like this. It's known as a sigmoid curve. And this was suggested by Zimdal. In 1982. So if you relate weed density versus crop yield, you get a decrease in yield. But during the first part, or if you have low weed densities, crop yield changes are very slow. Then suddenly you have got an increase. You have got a large decrease in yield. Then it tails off, and it gives us this sigmoid curve, a slanted S-shaped curve. Now let's see if we were to plot crop yield loss versus weed density. So crop yield loss as a percentage Okay. So here we've got width density. Again, there's a certain density which is up to this point. Where crop yield loss is low, but suddenly from this point you get an increase. We call this point weed control threshold. The loss is very low. It's low here. Here it's high. So probably we can start controlling weeds as soon as we reach the weed control threshold. This was according to Zimdar. In 1982. But Cousins proposed the following relationship. Now, according to Cousins, you have a rectangular hyperbola. That is the name of this curve. Whereas Zimdar proposed the sigmoid curve. And you can see, according to Cousins, there is no delay in losses, as suggested by Zimdar. With Cousins, immediately there is a serious loss once you get the weeds infecting your field. So let us look at what Cousins proposed as the weed loss graph. Crop yield loss. So according to Cousins, you get this loss. $19.85. Okay. So from Zimdar, this graph, there's a delay, and you can clearly identify the width control threshold. But from Cousins, there's no delay. As long as they are width, you get serious with you get serious crop loss. In contrast to this proposal by Zimdar, where there's a delay in loss, and you can clearly identify the width control threshold. This then seems to suggest that Cousins is saying that as long as you have widths, you need to control them according to this model. So from this model, we can identify two things. We can compute a parameter A, which is the maximum yield loss. We can also compute the slope, which is represented by I, on this graph. So for a particular width, it will have a value of A, maximum yield loss, and a value of I, which is the slope. So Cousins' model is the one which is usually used in width management, although we can use both models. The Zimdar one, which can clearly identify the width control threshold. Now, according to Cousins, you can work out the yield loss if we represent it by YL. It is equivalent to this dW multiplied by I, multiplied by the slope. So we can put I, which is the slope, and the density dw over 1 plus, or in brackets, I dw over this A, maximum yield loss. So this equation can actually estimate the crop yield loss when you are trying to determine the weed density, which affect crop yields. Remember, this is coming from the additive experiment. When you have done your experiment, you get your weed density and yield. You can also estimate crop yield loss and come up with this sort of graph. You can also come up with this equation from Cousins. Now, if we come to this graph, we can easily identify this. The weed control threshold, it's clear from this, because during the early stages, or where you have low weed density, it is not actually affecting the crop yields, or it has no impact on crop yield loss. But after a certain density, going this direction, you have an increase in crop yield loss. But on Cousins' graph, straight away there's a loss. So what if we want to get the weed control threshold? As a farm manager or agronomist, you may say probably 5% is not serious loss. So you mark 5% on your graph and come up with a density here. Now that density, which is represented by this dot, is your weed control threshold, because you have used your knowledge as an agronomist or as a farm manager to say that probably 5% is not serious, and the 5% yield loss could translate into this density. This becomes your weed control threshold. This is the density. If it is attained in the field, you now need to come in with the weed control regimes. But from Zimdal, you can easily read off the weed control threshold because of this sigmoid curve. So please note, there are two approaches to evaluate the effect of weed density in crops. You can use the Zimdal approach, or the cousins approach. The two graphs are contrasting, you know, they are not the same. Zimdaro has got a sigmoid curve, whereas cousins has got a rectangular hyperbola. So this is a rectangular hyperbola. Rectangular hyperbola. And please note that equation, which you can also use to estimate yield loss, which is you multiply the slope times density, or I times dW, you divide it by 1 plus, or in brackets, I times dW over A, which is the maximum yield loss. Let me answer this one. Hello? Yeah, I'm in the middle of a lecture. Okay, sorry for the disturbance. Now, let us explore again the cousins approach, the equation which he used. So, according to cousins, (1985), he defined yield loss as slope from the graph over 1 plus, or in brackets, IDW over A. But this part here is affected by weed seedling emergence. What it means is that weeds which can emerge before the crop will affect this prediction. This equation will not work well. So it has to take into account the weed seedling emergence factor. So he had to modify this equation like this. IDW did not change here, but 1 was replaced by E, which is the natural logarithm to the power of a constant multiplied by time. This time is the time of weed seedling emergence. Then he added this to this original part. Then the equation could predict any situation in a given field. You could predict the loss. So E is just the natural logarithm. C is just a constant, and T is time of weed seedling emergence. Weed seedling emergence. Okay, so using this equation in that manner, we can really predict the crop yield loss equation. And please note, we have got two approaches. The approach by Zimdal. Actually, the approach by Zimdal depends on the number of treatments which you have. If you have got many treatments, probably you end up using the Zimdal model. If there are few treatments, probably you end up using Cousin's model. And please note, we do have packages, software rather. We can have a computer software. For data analysis, usually sigma plot is good for this work. It has good regression analysis, you know. But other packages can also do the same. Now, we have talked of weed density. We've talked of weed density, and there's Zimdal, and Cousins. Now, there are scientists who think that probably weed density could be difficult to work with. So they have suggested this is DW, relative leaf area. which is represented by LW. So instead of relating crop yield and crop yield losses to weed density, we can relate these to relative leaf area of the weeds in the field. This was proposed by two scientists, Croft, difficult name, and Spitters, 1991. The use of relative leaf area. But we have found that working with another parameter known as relative cover could simplify issues, or RC. So we have talked about this with density, and we have gone through all these. Now we want to find out what Croft and Spitters found in 1991. In fact, why Croft and Spitters suggested use of relative cover, they wanted to solve this problem here, which was altered by Cousins in his equations, where he was substituting 1 with a logarithmic function raised to the power of a constant multiplied by time of weed seedling emergence. So they thought probably they could simplify issues by putting something easier, like leaf area, relative leaf area could simplify this time of weed seedling emergence factor. That's why they came up with another proposal. So how they estimated leaf area, relative leaf area, which is relative leaf area LW so they said relative leaf area is equivalent to leaf area index of weeds over leaf area index of the crop plus leaf area index of the weed. So this is leaf area index of weed Okay, sorry about that. So we've got leaf area index of the crop. So this is how they determined the leaf area, relative leaf area. You need to measure leaf area index of the weed, leaf area index of the crop. Then using that ratio, you get a relative leaf area. I don't know whether this is easy or even more complicated. Because simply counting weeds, just counting weeds could be easy. Measuring leaf area maybe it's something else. So they draw if you draw a graph to relate relative leaf area to yield loss, we just go straight to yield loss. So LW, this is the relative leaf area. Then we have a crop yield loss. Again, we get a rectangular hyperbola similar to Cousins, which means this approach could be good. Now we could get two parameters from this graph. Two parameters. A, but this one they called it Q instead of I. Now for yield loss, they multiply the Q, which is the slope, by relative leaf area, which is L W over, then they put a 1 here, plus, or in brackets, Q over A. A is the maximum yield loss. There's 1 here. Then they subtracted 1 from that quantity. Again, they multiplied it by LW. So this is how splitters, Croft, and splitters they suggested this equation. They said it was a better predictor of crop yield, maybe better than Cousins. So in this case, relative leaf area is now being used to substitute weed density. But probably a relative cover could be easy to use because you just use your estimation as you walk within the field. Relative cover RC. So RC was defined as W over C plus W. This is the area of weeds. By by weeds. Area covered by crop. So let us draw a graph using this parameter to substitute for weed density or for relative leaf area. So RC, relative cover, is now down here. Then crop yield loss. Again, A is here. This remains Q, and again yield loss would be predicted like this. Q over A minus 1. We'll put RC. If I go back here, if we wanted the weed control threshold, we could say just 5% will come here. That could give us weed control threshold. Which could be the relative leaf area which justifies weed control. And here we can also determine the relative cover which justifies weed control. So using the additive experiment, you can use weed density and pick Cousin's approach or Zimdal's approach. But under field conditions, you could use Croft and Spitter's approach and work out yield losses. So we're back to the relationships. Probably you now have an idea. Now the effect of weed density on crop yield. What is the density which justifies control of weeds in order to avoid economic yield loss? Do you think it's necessary to monitor weed populations in cropping field? in order to plan weed control programs, I think it is we should do this. Is weed density the best tool for predicting crop yield loss? We can use relative leaf area, we can use relative cover. Is data collected from one weed species applicable to fields with mixed weeds? That is another problem. So this is the relationship of weed density and crop yield, the sigmoid curve for Zimdal. Again, crop yield loss from the Zimdal approach. There's a delay at the beginning, but crop yield loss will shoot up. This is according to Cousins, where you have a rectangular hyperbola. If you draw crop yield versus weed density, and this is the crop yield loss with the weed density, and we can identify A and I parameters. The slope is I, A is maximum yield loss. And that is the equation which was proposed by Cousins, and we said that this one which is there will be a problem in the equation if weed emergence occurs earlier than the crop, and that had to be corrected by that logarithm, which I have actually explained this. Now, for your own information, we have got this table with different weeds in different crops, and we have got A and I values for different weeds, which we can use to compare their competitive abilities. So once we have this data, we can have more knowledge on how to approach with the control problems. This is the Croft and Spitters approach in 1991, which I have also explained. I have not go through it. And you get this sort of graph and that equation. As I have explained this, I have also explained this equation. The relative cover with students, they find the relative cover approach to be easier when they compare the three methods. Again, similar, the same equation which I have explained this in detail. If you can get a paper by Roger Cousins, a simple model relating yield loss to weed density. Then another paper by Croft and Spitters, a simple model of crop loss by weed competition from early observations on the relative leaf area of weeds. These are some of the references which you may read. They did similar work. Now, what are the disadvantages of the additive design? Well, crop biomass varies with the species proportion and density. This can cause some problems when assessing the results. The competitiveness of the crop is not determined. Now, it does not separate intra and interspecific competition. These are disadvantages. Now, which brings us to the next issue. Well, you can do this in glass houses, this type of experiments which I was explaining. Now, weed control thresholds in Southern Africa, very little research has been done on weed control thresholds in Southern Africa. The first flush of weeds in summer appears to exceed weed control thresholds. Therefore, weed control is always necessary. The second and subsequent flushes of weeds in summer appear to be below weed control thresholds. But there's a need to do some work. Probably I should mention that we do have a DPhil student who is working in Murewa and Mutoko, and from the data which she has collected so far, I think we can come up with some weed control thresholds for those two areas, specifically for maize and groundnuts. Probably it's still early, the data is still being analyzed, quite a lot of data, but I think we will get somewhere and come up with some weed control thresholds for those smallholder farming areas. Now, in winter cereals, in most cases, weed seedling emergence appear to be below weed control thresholds. Probably it's because of frost. Now we move on to the second important experiments, the replacement series. Now the questions which we wanted to ask is, what is the competitive ability of plant species in a mixture? Actually, the right question which we are interested in is, what is the competitive ability of the weeds and the crops? With the additive experiment, we can only get more information on weeds and not on crops. So, how do we conduct a replacement series experiment? The other name for replacement series is substitutive experiment. Now, the species proportions are varied, but the species total is maintained. I will demonstrate this statement. In a mixture involving A species and the B species, for example, we can increase the number of A species from 0 to X, and at the same time we can decrease that of B from X to 0. Let us use the example of maize and rapoko grass. That structure, we call it the binary structure, where we can start with the maize. We have got 0, and the number of rapoko grass will be 10 if we have maize as 0. If we increase the number of maize plants to 2, we have the proportion of grass to 8, then 4 and 6, 5 and 5, 6 and 4, 8 and 2, and 10 and 0. I hope it's clear from where you are. We call this the binary structure, and this is what we normally use. Of course, you can increase the number of plants in the mixture, for example, like this known as the ternary structure. where you have 15 maize plants, you have 0 for Rapoco grass and Mexican clover. Then you come up with 15 Rapoco grass and you have 0 maize, 0 Mexican clover, or you end up with 15 Mexican clover, then 0 maize and 0 Rapoco grass. And you can have those proportions. But we are not going to follow the ternary structure. We will follow the binary structure. Please note that if you add the number of maize plants and the Rapoco plants, the total should always be 10. You can try it. You will find that the total is 10. Now, with the measurements, we are just interested in dry matter. And how are we going to use dry matter? Probably I will need to explain this again in stages so that you'll be able to understand it. If I give you everything, you may not understand it. So I wanted to use dry matter and explain how we can get information out of the replacement series. Remember, we wanted to find the competitive ability of the weed and the crop. These are the main issues. So we are talking of replacement series experiments. With objective Come in, competitive ability. Come in. Yeah. Ability of I'm in a class actually. I'm teaching. Okay.
So when
after one maybe. To determine the competitive ability of the weed and the crop. So we need a dry matter. Now, what we are going to use, number one, we will need what are known as replacement series diagrams. Number two, we will need relative yield. I will shorten it. Relative yield of crop, which is yield of crop in mixture over yield of crop in soil crop or in pure crop. Then RYW, yield of wheat over in mixture over yield of wheat in soil. Then the other thing which we need is total relative yield total, which is RY crop plus RY wheat. Now, if this is equal to 1, it means no competition. Equal competition. Sorry. Equal less than 1 it means the plants are antagonistic to each other, the weed and the crop. If it is more than one, it means synergism. Then there's another parameter known as relative crowding coefficient, RCC. Another one is aggressivity, or simply AGR. So if we want to assess the replacement series diagram, I mean the replacement series experiment, we are going to use the dry matter to draw replacement series diagrams. They will give us information on the competitive ability of the two plants. We are also going to calculate the relative yield of the crop as indicated, also the relative yield of the wheat as indicated. And later on we'll also calculate the RCC, the relative crowding coefficient, and see what it means in terms of competitive ability. This same applies to this parameter aggressivity, AGR, what it will mean in terms of competitive ability of either the weed or the crop. So we are going to start off with the replacement series diagrams, because these are the ones which you can use to derive information on competitive ability. Remember, after carrying out this replacement series experiment, your objective is to determine the competitive ability of either the weed or the crop. And this is how you are going to do it. First, you use the replacement series diagram. Replacement series diagram. You will need a graph like this. Actually, there are two graphs which are superimposed. So for the crop, let me just use C to represent the crop. And for your x-axis, your crop, you can start with 0 and probably increase up to 100. Of course, you can have low numbers. Then the weed may start with 100 and decrease to 0. Let us have a case of the crop. As we increase the numbers up to 100, maybe the dry matter will increase. So on the y-axis for the crop, let us put it here. We put relative yield of the crop. So this is against relative yield. Again here it's against relative yield of the wheat. So as we increase, this will also increase, maybe up to this point. Right, in a straight line like that. As for the wheat, we are starting from the top and decreasing to 0. Up to there. That is for the wheat. And this line on top, we call it the RYT, relative yield total. This is the sum of RYC and RYW. Now, when we get such a structure, this is scenario number 1, or outcome number 1. When we have straight lines for C and straight line for W, it means there is equal competition. And this is an example of a replacement series diagram. It means equal competition. Let us move to a scenario 2. Number 2, we can have this sort of outcome. Again, we have our C. Now for the crop, we may have something like this. Which is a departure. And we say this is C is actually concave. It has a concave shape. Now, as for the wheat, which starts from the top, it may end up like this. And its shape is described as convex. And this, we are not worried at the moment about the RYT, which is the relative yield total. When you have the crop being concave and the weed being convex, we say the weed is more competitive than the crop. So W is more competitive than C. Remember, you are working with the dry matter measured from that experiment, the replacement series experiment. Now what it is saying is that the crop is less competitive than the wheat. Let us move to the third scenario. We still have our C here, starting from 0, going to 100. Our weed starting from 100, decreasing to 0. And on the y-axis, we still have our crop here. Our weed here. Now let us look at the crop. Now instead of the crop going under this expected line, it goes above it. Now it is convex. Let us check. This now becomes under the expected output. This is W. It is now concave. Yeah, we're just looking at the shapes of those lines. If it is concave, it means less competitive. Convex means more competitive. And then we will have this is our RYT. So in this scenario, the crop represented by C is more competitive than W. It's a changed scenario. Let's move on to outcome number 4, sorry. Outcome number 4. C starts from 0, going to 100. W from 100, going to 0. RY C. RY W. Let us start with the crop. Instead of having a straight line, the crop has been affected. It's underperforming. Again, we get C, which is concave. We go to the weed. We expect a straight line there. Again, we get underperformance. which is again a concave. So both W and C are giving us the concaves. And let us look at the relative yield total. It's also a concave. It has gone inside. Now, this kind of a scenario where everything is concave, where everything is concave, we call this an antagonism. We call this antagonism. Perhaps this is a situation where you have areopathy at play, and both species are being affected. So, hapana chinobuda in this relationship, because everything is not working. The last one is this one. Number 5. Let's see what we are going to come up with. Right. C starts from 0 going to 100. W starts from 100 going to 0. RY, C, we start from the crop. The crop is having good performance, exceeds the expected dry matter output. Convex, let us look at the weed. Also, it outperforms. Again, convex, and yield total. Again, convex. This is what we call synergism. What I must say is that this is a rare outcome of synergism, Normally, the previous cases which I have described are common in the weed crop interaction. This one where we have synergism is rare. So please remember these 5 outcomes: equal competition. Here we have the weed being more competitive, the crop being more competitive. Both the crop and the weed are suffering in antagonism, and in synergism they are both benefiting from the association. Now let me move on to the other assessment which we can do. Where we can use this term we can also use, we have used replacement series diagrams to indicate which species is more competitive than the other by simply observing what is happening to the diagram or model. We can also use this the relative crowding coefficient, or RCC. Now we can calculate the values separately for the components in a mixture. Let's start with the crop. RCC crop. We get it from this equation. We want the yield of crop. I'll just say C in mixture over yield of wheat represented by W in mixture. We put this in brackets. When we have a value, we divide it by yield of crop in pure stand or soil. Yield of wheat in soil. That will give us a value for the crop. We can also do it for the wheat. RCC wheat. Now in this case we have yield of wheat in mixture over yield of crop in mixture. All this in brackets divided by yield of weed in sow, over yield of crop in sow, everything in brackets. So if we work out these programs, if you want, we should arrive at certain values. Let's suppose RCC is 1. This means equal competition. The competitive ability of the weed and the crop are the same. If it is less than 1, it depends whether it is RCC weed or RCC crop. It means the one which you have calculated for this value is less competitive, or it could be more competitive, depending which value you have computed, because you have RCC maize or RCC crop, RCC wheat. So it depends which one you are working out. If you get those values, that's what it means in terms of competitive ability. We now move on to the last item under replacement series experiments, which we can also evaluate competitive ability. We call it aggressivity. Aggressivity AGR. Now, if we wanted the aggressivity for the weed, okay, let's say crop. It will be 0.5 multiplied by bracket relative yield crop minus relative yield weed. AGR weed multiplied by, this time it's in reverse. Right. If you get 0, it means no competition. A negative value means less competitive. It depends which one in which you have competed. Is it AGR crop or AGR wheat? It could be a positive number, which means more competitive. So this is how you can assess the results from the replacement series diagrams, I mean experiments rather. So we switch off from this coming. So we're here. Yeah. So this is how you can process the dry matter or biomass into something meaningful. This is what I went through with you. We said you can use replacement series diagrams, use competitive indices. This is the competitive indices which I have calculated relative crowding coefficient and aggressivity. Although there are more than 50 indices, in our case we just use 2, RCC and AGR. Relative yield total, I've shown you how to calculate these. These are the outcomes from replacement series diagrams. If you get that one, it means no competition. Here, B is more competitive than A. A is now more competitive than B because of the curvatures of those lines. Here, there is antagonism. Everything is in a concave position. Here we have got a synergism or probably symbiotic relationship. It's the other word, symbiosis or synergism, where everything is outperforming the expected. You can read this paper, a replacement series, evaluation of rice and the weed called the barnyard grass. These are the sort of results which you are going to see, and they will indicate which plant is more competitive than the other. You look at the expected dotted line, whether it's what you have found is above it or below it, then it will give you the indication of the competition status. Another paper, relative competitiveness of irrigated rice cultivars and that wheat. In other words, you can actually run or you can test various cultivars against one wheat and end up giving us the crop or the genotype which is tolerant to weed infestation. This is how we can identify tolerance for weed competition. We can use the replacement series experiment. These are the sort of outcomes which I was showing you. We don't need to go into details. Go and read that paper. If you are interested, you will be able to understand what is going on. Key references. There's also a paper by Chivinge and Schwepenhauser who were working on pig wheat, which they found to be more competitive than blackjack. In fact, Chivinge did his PhD on this issue, being supervised by Professor Schwepenhauser. Then Professor Chivinge also supervised Rupende in 1997, who worked on Rapoko grass, which was now more competitive than Mexican clover. They were using these methodologies, replacement series diagrams. So in a summary, these are the sort of outcomes in terms of replacement series diagrams. There are 5 likely outcomes should you conduct this experiment. Other parameters, I've explained them. ROIC, relative yield of the crop, which is yield of the crop grown in mixture divided by yield of the crop in pure state. Relative yield of the weed, RYW, is equal to the yield of the weed grown in mixture divided by the yield of the weed in a pure state. And the relative yield total is the sum of ROIC and RYW. I've already explained what this means. If you get 1, it means equal competition, less than 1 antagonism, more than 1 synergism or symbiosis. This is the relative crowding coefficient for maize. This is how you do it. This is the relative coefficient for rapoko in a mixture of maize and rapoko. This is how you do it. If you have a 1, it means equal competition. More than 1, one of the species is more competitive. Less than 1, one of the species is less competitive. Yeah, you come to understand this. Aggressivity, I've explained it. For maize, relative yield of maize minus relative yield of rapoko multiplied by 0.5. You do the same with rapoko. If you get 0, it means equal competition. Otherwise, the outcome could be positive or negative. If it is positive, it means strong competition. Negative, low competition, something like that. The disadvantage is that the study is done at one density and cannot be extrapolated to other densities. But I think it can give us sufficient information if we are interested to compare different cultivars, or simply just to find out whether the wheat is more competitive than the crop. Of course, there are other experiments which can be improved upon this basic replacement series diagram. So what we have just done is to focus on additive designs or additive experiments, which I think you may want to use. Then replacement series designs or experiments, which I think they are also relevant. I have left out other issues or other studies which I think may not be of interest to breeders or agronomists. Those ones may be interested for wheat scientists. The indices for plant competition we have described. Aggressivity, actually it was originated by McGill Christ in 1965. Relative crowding coefficient was originated by DeWitt in 1960. Then it was promoted by Cousins and O'Neill in 1993. The concept of relative yield, again from DeWitt, 1960, DeWitt and Van Den Berg in 1965. Relative yield total, again by the same authors. The replacement series or substitutive experiments are also commonly used in intercropping studies, where you may combine maize, cowpea, or maize and groundnuts. This is it on the effect of density. So let me